Hello, Maurits here. In this video we should look at the area enclosed between two functions and possibly some start value of the interval and end value of the interval. Let's say we have two functions, f of x and another function, g of x, and from a to b, and our problem is to find this area here. In principle, what we can do is to find the area underneath the f of x minus the area underneath g of x, and that will give us the area. So we can write an expression for this. So the integral from a to b of f of x dx minus the integral from a to b of g of x with respect to x. But we can also save a bit of time quite often by instead evaluate this integral, the integral from a to b of f of x minus g of x with respect to x. And in principle what we do is that we instead will add up little areas like this, where the width of this is delta x and the height now is f of x minus g of x, right? So we create a new function that just gives us the difference in height. The advantage with this is that we don't need to care about if one of the function happened to dip down below 0, because this value minus that value will still give you the length in between, the distance in between the two graphs. Let's look at a couple of examples. Say that f of x equals to x squared plus 2 and g of x equals to x squared, and a is 0 and b is 2. Okay, so we get the integral from 0 to 2 of the first function, x squared plus 2, that is our f of x, right? Minus second function, that is g of x, that is x squared. So this is g of x with respect to x, and we can see here that the x squared and x squared happen to cancel. So we get the integral from 0 to 2 of just 2 dx. And that is very easy to evaluate, right? The primitive function, or the antiderivative of 2, is just 2x. From 0 to 2, plug in 2 to this. That will give us 2 times 2. Plug in 0 to this. That will be 2 times 0. And that will give 4 all in all. This will really make sense if we graph the functions. So we have 1, 2, 3, 4, 5, 6. 1, 2. And we look at the x squared plus 2. 0 gives us 2. 1 gives us 1 squared plus 2, that's 3. And 2 gives us 2 squared, that's 4, plus 2, that's 6. So the graph looks something like this, and the x squared curve, we know, will just be something like this. And the distance between these two curves will be constant, and that is 2. So that's why we get that we integrate from 0 to 2 of 2 dx, because the difference is all the way 2. So this is the same thing as the area of a rectangle or square that is 2 by 2. We can imagine that we can get to this area here by taking this area and just stretch it a bit up like this, right? That area, since the distance between the top and bottom value is equally big all the way through, the area won't change, just the shape of it. Okay, so let's look at another example. We should look at f of x equals to 8 minus x squared, and say g of x equals to x squared. and we should find the area enclosed between these two. So the first thing we could do is try to graph this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2. So if we plug in 0 to f of x, we get 8. 1 gives us 7, and same thing with -1. And 2 gives us 4, right? Because 8 minus 2 squared, that's 8 minus 4. 1, 2, 3, 4. So we're down here, right? 1, 2, 3, 4. And same thing on this side. So we get an upside down parabola, something like this. And if we look at the x square, it looks just the same, but upside down. Okay, we can also see that these two will cross each other at 2 and -2. If we didn't graph it, we could still figure this out by putting the two equations equal to each other. Add x squared on both sides. Divide by 2. Square root both sides, so that will give us plus -2 is our x value, just as expected. So we need to find the integral from -2 to 2 of the first function, that is 8 minus x squared, minus the second function, that is x squared, that will give us the integral from -2 to 2 of 8 minus 2x squared with respect to x. We need to find the antiderivative of 8. It's 8x, right? We keep the -2. Remember this, we keep a constant we multiply by. And x squared will give us x to the power 3 over 3 from -2 to 2. Plugging in the 2 to this. 8 times 2 minus 2 times 2 to the power 3 over 3 minus, and plugging in -2 to this, 8 times -2 minus 2 times -2 to the power of 3 over 2 equals 8 times 2, that's 16. 2 to the power of 3, that's 8 times -2. Okay, so this will become -16 over 3. Minus 8 times -2, that's -16. And then -2 to the power of 3, that's -8 times -2. Oh, so that will become plus 16 over 3. Getting rid of the brackets here. 16 minus 16 thirds minus minus, that is plus 16 minus 16 thirds. 32 minus 32 thirds. Write in everything in thirds. 32 times 3 over 3 minus 32 over 3. 32 times 3 minus 32. That will just give us 64, right? Over 3. And we might notice that this is twice the answer on a previous integral we did. Remember this, that we had the problem 4 minus x squared. 1, 2, 3, 4. And that was this shape, right? And as we can see, that is exactly this shape, just shifted up 4 steps. So they will be the same. The area of this is the same as the area of this. And since the lower part of the graph, this half, is just the other one upside down, it will be the same area, so the area will be twice of this. And as we saw previously, the area of this is 32 over 3, and that times 2 is 64 over 3. We could even make it easier for ourselves, because you remember this, we could integrate just get this quarter here, and if we take that fourth and multiply it by 4, then we get a total area. So that could be a bit of simplification. But if we don't have time to figure this out on an exam, we can just do the integral like this. Okay, then we should look at an example, yet another example, but here we need to use the calculator. Say we have the two functions f of x equals to 2 to the power of x, and g of x equals to x squared. Let's try to graph that. We know the x squared curve looks something like this, right? And the 2 to the power of x looks something like this, and they will cross each other again here. We can actually figure out these 2 points fairly easy, because if we take 2 to the power of x should be equal to x to the power 2, we can see that 2 must be a solution. So if x is 2, we get 2 to the power 2 equals 2 to the power 2. Yay. And we can also see that if x is 4, we get 2 to the power of 4 is 16, but we also get that 4 to the power 2 is 16. So we know that this value here is 2 and this is 4. This point is a bit harder, and we can't really figure this one out without a calculator. I will start a calculator and enter my two functions. So 2 to the power of x and x squared. Draw, and we get this here, and this is the point we're interested in. We can actually zoom out here. I will put window and put my y max to say 20, because we know that we must go to at least 16. Exit, draw, and this is one of the two bubbles we want to work with, and this should be another one. So actually what we would do here is go to gsolve, intersection. We find the first one at minus 0.76666. So minus 0.76666 and 47. Okay, so we need to do two integrals here, because we can see that for the first part 2 to the power of x is larger, and for the second part x squared is the larger one. So we do one integral from minus 0.76667 to 2 of 2 to the power of x minus x squared with respect to x. We do that on the calculator. So we need to find this integral. By the way, there should be one extra 6 there that I missed. So we take the integral of 2 to the power of x minus x squared from minus 0.7666647 to 2. And we find an area of 2.106. I will store this in a variable, say b. So store alpha b. And then we need to do a second integral. We need to integrate between 2 and 4. And as we can see here, the x squared is now the topmost function. So we take x squared minus 2 to the power of x with respect to x. So yet again with the calculator, the integral of x squared minus 2 to the power of x from 2 to 4. And we get 1.354. 1.354. We add b to this, so plus alpha b, and that will give us a total enclosed area of 3.46. We round to three significant figures, 3.46. So we have solved the problem. So if you have two functions and it is a paper 2, you have access to the calculator, graph the functions. Even if it's not a paper 2, just try to graph the function or the functions and see if they intersect at some points, because you might have to split this into different integrals. Not too common, but it happens. And it can be more parts, but usually it's either one or two enclosed areas. And then a really good tip is to store in between variables values into the variables, and you can write something like this to remember where you put it. You can also write here, okay, this is B, why not call this C here if you want to, so we know what we are doing. Hope this helped a bit. Thank you.